Before telescopes, before equations, some of the oldest human texts opened with the same kind of sentence. In the beginning, a single doorway phrase, offered with total confidence, as if reality itself had a first page. Modern cosmology gave that doorway a new name, the Big Bang. A hot, dense, early state, expanding into everything we see. And for a long time, it was easy to let the story harden into something even stronger than science ever promised. The idea that the universe truly began there, that time itself started, and nothing existed before. But what if that isn't the right picture? What if the Big Bang is not the first moment of reality, but the first moment our current map can describe? A boundary where our best equations stop. Not necessarily where existence stops. A curtain, not a wall. This is the question at the heart of this film. What would it mean scientifically if the universe did not start with the Big Bang? Stay with it, and three things will become clear. First, what the Big Bang model genuinely explains and what it doesn't claim. Second, the serious scientific pathways that allow a universe with no first, second, from cosmic bounces to deeper space-time extensions. And third, a quieter reward. A new way to locate yourself inside a cosmos whose origin may be less like an explosion and more like a horizon. To even ask whether the universe did not start with the Big Bang, we have to walk straight through the version of the story most of us already carry in our heads and see where it quietly stops talking. So this first step is not to overthrow anything, but to listen more carefully to what we think we already know. If you close your eyes and imagine the usual story, it often begins like this. Space itself is expanding. The galaxies are drifting apart, carried by that expansion like specks of dust in a swelling loaf of bread. If we hit rewind on that cosmic film, everything runs backward. Galaxies draw closer together. Distances shrink. Temperatures rise. Matter that is now spread across unimaginable scales gets squeezed tighter and tighter into a smaller region. Follow that mental movie far enough, and the picture becomes extreme. Every star, every planet, every atom, every photon, every field line, all the energy and matter in the observable universe, crushed into what the simplest version of the model calls a single point of infinite density and curvature. Then, in the popular image, something happens. A sudden release, an enormous expansion. Time itself, people say, starts. That is the Big Bang, as it often lives in culture, a single moment, the first frame of the universe's film. Physics did not arrive at that image all at once. It walked there, slowly, step by step. In the early years of the 20th century, the universe was still imagined as essentially static, eternal, a kind of grand, unmoving stage on which local dramas played out. Stars formed and died, nebulae glowed and faded, but overall, the cosmos was thought to be steady. Then came Albert Einstein, with the field equations of general relativity in the middle of the 19-teens. Gravity, in this new picture, was no longer a force acting at a distance in a fixed space. It was the geometry of space-time itself. Mass and energy told space-time how to curve. Curved space-time told matter how to move. Left to themselves, those equations did not describe a static universe. They wanted space, as a whole, to do something, to expand or to contract. Einstein, guided by his intuition that the cosmos should be stable on the largest scales, added an extra term, the cosmological constant, tuned just so to hold the universe in balance. It was an elegant adjustment. It also quietly fought against what his own equations were trying to say. A few years later, others took those same equations and were less interested in protecting a static picture. Alexander Friedmann, in the early 1920s, found solutions in which space is not held fixed at all. The scale of the universe can grow or shrink with time. Georges Lemaitre, a Belgian priest and physicist, picked up that thread a few years later. He connected these expanding solutions to actual astronomical observations of nebulae that seemed to be flying apart. On paper, a new possibility appeared. Maybe the universe has a history. Not just local change, but a global evolution of space itself. What had been, for Einstein, a mathematical inconvenience became, for Friedman and Lemaitre, a feature. If space is expanding today, then yesterday it was smaller. The day before, smaller still. And if you keep following that logic backward, you do not simply get to very small. In the simplest version, the scale factor of the universe shrinks all the way to zero. Volumes vanish. Densities blow up. That limiting state is what later came to be called a singularity. For a while, this was mostly theory. A set of possible worlds living inside differential equations. The sky still had to vote. In the last year of the 1920s, Edwin Hubble measured the light from distant galaxies with the 100-inch telescope on Mount Wilson in California. He noticed something systematic. The farther away a galaxy was, the more its light was stretched toward the red end of the spectrum. You can think of it as cosmic Doppler shift, like the lowering pitch of a siren as an ambulance drives away. But now, with the wavelength of starlight, those redshifts lined up in a pattern. Distance and recession speed rose together in a nearly straight line. It was as if all the galaxies were receding from each other, not because they had been flung through space, but because the fabric of space between them was expanding. A mathematical possibility had become a physical story. The universe is expanding. Run that story backward in time, and you do not just get a poetic idea of long ago. You get a precise, compressing history. Each earlier slice of cosmic time has galaxies closer together, radiation more energetic, matter more tightly coupled. In that rewind, the film does not gently fade to black. It runs into a final frame, where the simplest model says, "Here, our scale factor is zero. Here, densities are infinite. Here, curvature diverges. A singularity. If you draw it on paper, all the world lines of matter converge to a single sharp point in a space-time diagram. A universe born from a point. And yet, even at this stage, we are still just following the internal logic of an equation. Beautiful, powerful, but alone. In the mid-1960s, two radio engineers at Bell Labs, Arno Penzias and Robert Wilson, were trying to clean up the signal from a horn antenna in New Jersey. They were not hunting for the origin of the universe. They were hunting for noise in their instrument. No matter what they did, a faint, uniform hiss remained. It did not go away when they pointed the antenna at different parts of the sky. It did not seem to come from the Milky Way. It was just there, a soft, persistent glow in the microwave part of the spectrum. What they had stumbled on was not local interference. It was the afterglow of a hot, dense early universe, stretched and cooled by expansion until it now bathes all of space in microwave light at a temperature of about 3 degrees above absolute zero on the Kelvin scale. The cosmic microwave background. This radiation is astonishingly uniform. Look in any direction and you see almost the same temperature. Only tiny ripples, parts in 100,000, disturb an otherwise smooth glow. That is exactly what you would expect if the cosmos, long ago, had been in a nearly uniform, very hot plasma state before it expanded and cooled enough for neutral atoms to form and light to travel freely. Suddenly, the idea of a hot, dense, early phase stopped being a speculative add-on and became something like an observational fact. The sky itself remembers. Another line of evidence came from the lightest elements. In the 1940s and 1950s, George Gamow and collaborators worked out what should happen if, in the first few minutes of cosmic history, the universe was hot and dense enough for nuclear reactions to fuse protons and neutrons together. They predicted that such a phase would leave behind a cosmos composed mostly of hydrogen, with roughly a quarter of its mass in helium and only traces of heavier elements. When astronomers looked at the composition of old stars and diffuse gas, that is exactly what they found. The universe carries the chemical signature of having once been in the kind of furnace those calculations describe. Taken together, these clues form a remarkably coherent picture. An expanding universe, seen in galaxy redshifts. A faint microwave afterglow, seen across the whole sky. A specific mix of light elements, written into stars and gas. They all point back to a time when the cosmos was smaller, hotter, denser, and more uniform than it is now. The Big Bang model, in this sober sense, is a way of describing that early hot phase and how it evolves forward using general relativity and nuclear physics. It is already amazing that such a thing can be done at all. That we can infer, with some confidence, conditions that held when the universe was a fraction of its present age, at densities and temperatures far beyond anything we can reach on Earth. But the human mind, once it has a story, tends to polish it, to fill in gaps with something smoother, more complete. Somewhere between the physics papers and the way the story is told at dinner tables, in documentaries, in science fiction, a subtle shift happened. The Big Bang stopped being simply a hot, dense, early state from which the observable universe expanded, and became, in many people's minds, the moment when everything came from nothing. An absolute beginning. Time equals zero. Before that, nothing, not even time. The equations, however, are quieter than that. When cosmologists draw these models, they often mark time with a parameter that runs backward toward a value, where their idealized solution becomes singular. At that boundary, quantities like density or curvature diverge. In the simplest models, that value is labeled zero. But this zero is not a photograph of nothing. It is a place where the model breaks down, a point beyond which this particular set of equations no longer produces a meaningful answer. Our observations, for their part, do not touch that point directly. The cosmic microwave background we see today comes from a time when the universe was already transparent. A few 100,000 years after that hot phase began, the light element abundances come from nuclear reactions that took place minutes after those earliest moments. Even the most distant galaxies we have observed so far are seen hundreds of millions of years into the expansion. Everything we measure points back toward a hot, dense origin. None of it looks directly at the supposed first instant. This is the first quiet, destabilizing fact. The Big Bang, in the way physicists use the term, was never really a theory that everything emerged from literal nothingness. It is a description of an early state in which the densities and temperatures were so high that our current combination of general relativity and particle physics can still make sense of what is going on, at least for a while. The extra sentence, "and before that there was nothing," is mostly something we, as storytelling animals, have stapled on. You can feel the pull of that stapled sentence. We dislike open edges. We like clean origins. A first line to the book, even if the book is the universe itself. That desire for closure seeps into our images as well. In Christopher Nolan's film Interstellar, there is a scene where the main character falls into a black hole. The screen fills with whirling light. Space seems to fold and stretch. For a moment, it feels like we are entering some ultimate center, the heart of everything. Then the film does what stories often do at moments of extremity. It cuts away. It jumps to a different representation, a new set of images that allow the plot to continue. It is fiction, of course, but notice what the scene reveals about us. When we push our models to their limits, whether at the edge of a black hole or at the beginning of cosmic expansion, we instinctively imagine some deeper chamber beyond the door. We find it hard to accept that what we are really looking at might be the boundary of a description rather than the boundary of reality. The standard cosmological story, in its simplest Big Bang form, is like that film. It carries us, with impressive confidence, from the present back through galaxy evolution, through recombination, through primordial nucleosynthesis, all the way to a frame where the math writes a sharp point and then goes silent. We are tempted to label that point the first page because it is the first one our current tools can print. But if that is all it is, a limit of the tools, then the real question is stranger and more unsettling. If what we call the Big Bang is only the place where our present map tears, not necessarily where existence itself begins, have we been mistaking the first page we can read for the first page that is actually there? When you stare at that supposed first page long enough, you start to notice that the ink does not sit evenly. The simple picture of a universe born cleanly from a point begins to wrinkle under its own evidence. One of the strangest wrinkles is something you cannot see just by looking up, but it is hidden in the way the sky glows in microwaves. When satellites mapped the cosmic microwave background in detail, they found something almost unsettlingly simple. In every direction, the temperature is nearly the same. Not exactly, but so close that the differences are only a few parts in 100,000. On the surface, that sounds comforting. A calm, almost perfectly uniform baby universe. But if you take the standard Big Bang picture seriously and ask how far light could have traveled in the early cosmos, you discover a problem. Distant regions of the sky, sitting on opposite sides of the Earth, were never close enough to exchange signals in the time available before the light of the microwave background was released. They sit outside each other's light cones. There was no way, in that simple model, for information about temperature or density to move from one region to the other fast enough to bring them into such close agreement. Yet, when we measure them, they match to an absurd degree. It is like walking into a huge room full of people who have never met, who have never spoken, and discovering that every single one of them is wearing the same color shirt, the same shade of trousers, and humming the same tune in almost perfect synchrony. Not just roughly similar, almost identical. The ordinary Big Bang story says these regions were never in contact. The sky says otherwise. This puzzle is called the horizon problem. It is one of several that arise when you push the simple expanding from a point picture hard enough. Another, the flatness problem, asks why the geometry of the universe today is so close to the delicate balance point between overall positive curvature and overall negative curvature. A third, the relic problem, asks why certain heavy particles predicted by high-energy theories are not showing up in cosmic abundance. Each of these issues has its own technical life in equations and parameters. But emotionally, they rhyme. They all whisper that the initial conditions in the simple Big Bang story look improbably tuned. Everything starts off just so. In the late 1970s and early 1980s, a new idea emerged that tried to address these issues in a single stroke. It is called cosmic inflation. The bare idea is straightforward, even if some of its details are not. Instead of imagining the universe always expanding at a gentle, steady rate, inflation proposes that in its earliest fraction of a second, space went through a brief period of astonishingly rapid expansion. Not just fast in everyday terms, but exponentially fast, doubling its size again and again in a time so short that our ordinary intuitions do not have anywhere to stand. Why would that help? Imagine that. Before this rapid expansion, the universe was a tiny patch of space that had enough time to settle down. Temperatures evened out. Densities smoothed. Within that small region, everything could come into contact with everything else. They could share heat, exchange information, reach equilibrium. Then, inflation begins. Space itself stretches that tiny, smooth patch out to cosmic size. Regions that were once neighbors become separated by distances far beyond any light signal since then. The horizon problem disappears, not because these regions were never in contact, but because they were, long before the light of the microwave background was released. Their eerie matching is a fossil of that earlier intimacy. A common picture is the surface of a balloon. Draw a few specks of ink close together, let them jostle, come to some rough uniformity, and then start blowing up the balloon. As it swells, the specks move apart. What used to be a small, smooth region on your desk becomes an enormous, smooth region in the air. Inflation also helps with flatness. If you take any small patch of a curved surface and zoom in enough, it begins to look flat. A city feels flat to you, even if it lies on the curved surface of the Earth. If inflation magnifies a tiny patch of space-time to enormous size, the apparent curvature on that scale will look extremely close to zero. The universe appears flat, not because it is exactly so on the deepest level, but because we are living on a massively blown-up fragment. In this way, inflation does something deeply attractive. It takes what looked like unlikely initial conditions and tries to make them natural consequences of a dynamical process. Instead of assuming the universe began miraculously smooth and nearly flat, it says, perhaps it became that way because of what it did. Over the following decades, this idea was not left alone as a poetic sketch. It was fed into detailed models of how quantum fluctuations in fields during inflation would be stretched into macroscopic ripples in density. Those ripples, in turn, would seed the tiny temperature variations we see in the cosmic microwave background. And later, the formation of galaxies and clusters. Then the sky was asked to answer again. Satellite missions like the Wilkinson Microwave, Anisotropy Probe, and later the Planck Observatory mapped the microwave background with exquisite precision. They did not just confirm that the sky is uniform, they measured the pattern of its tiny deviations from uniformity across a wide range of angular scales. They weighed how strong the ripples are at different sizes. These maps give us something like the fingerprint of the early universe. Inflationary models make specific predictions about the statistical properties of those fingerprints, and remarkably, many of those predictions match what we see. The universe is very nearly spatially flat. The fluctuations are almost, but not exactly, scale invariant. They are nearly Gaussian in their statistics. The pattern is consistent with quantum fluctuations stretched by a rapid early expansion. Because of this, inflation has become part of what many cosmologists mean when they talk about the standard model of the universe. It is not just a clever patch slapped onto the Big Bang. It is woven into the way we interpret a wide range of data, from the microwave background to the large-scale distribution of galaxies. At the same time, inflation is not a single theory. It is a framework, a family of models. To make it concrete, you need to specify what field drives the expansion, what its potential energy looks like, how inflation ends, and how it hands over to the more familiar hot, dense phase described by the classic Big Bang equations. There are many ways to do that. Some are already ruled out by observation. Others remain viable. Some are baroque. A few are relatively simple. As cosmologists explored this landscape, another, more radical idea began to surface. In many models, inflation does not end everywhere at once. Instead, it stops in some region, dumping energy into particles and radiation, creating a hot, expanding bubble that can grow into a universe like ours, while inflation continues in other regions. Those regions, still inflating, can themselves spawn new bubbles later. This picture is called eternal inflation. In eternal inflation, there is always some part of the larger space-time that is inflating, and always some bubble universes being born where inflation has ceased locally. Inside each bubble, the physics can look different. The constants of nature might vary. The amount of dark energy might change. The vacuum state of underlying fields might be different. Each bubble becomes a pocket cosmos, with its own internal history and, perhaps, its own astronomers one day looking up and asking how it all began. From the perspective of observers inside a bubble like ours, the story feels familiar. There is a hot, dense early phase, cooling and expanding. Structure forms. Stars light up. The cosmic microwave background glows. But outside, beyond the bubble walls, the larger inflating space continues to grow and spawn further bubbles endlessly into its future. Once you draw that picture, a new question almost forces itself into being. If inflation can run without end into the future, can it also run without a beginning into the past? Could there have been inflating space stretching back indefinitely, with bubble universes budding off it forever? In that case, the Big Bang inside our bubble would not be the first moment of existence. It would be a local event, a warm, brief flash on the skin of an eternal inflating sea. This is one of the most amazing conceptual shifts inflation brought with it. A mechanism originally proposed to tidy up the initial conditions of the Big Bang ends up turning the whole notion of initial into a question mark. The sky, again, plays a double role here. High-precision measurements of the cosmic microwave background and large-scale structure keep pushing inflation into a narrower corner of possibility space. They tell us that whatever happened in those earliest moments has to produce the specific spectrum of fluctuations we see, almost scale invariant, with just the right tilt, and a specific pattern of acoustic peaks. They also tell us what we do not see. No strong signs of exotic, non-Gaussian features, no large primordial gravitational wave signals so far, no obvious scars of violent pre-inflationary events. Within that corner, many models still fit. Some predict eternal inflation, some do not. Some suggest our bubble universe is one of countless others. Some keep the picture more modest. At the same time, the data are not perfectly smooth. The Planck maps, for instance, reveal a mysterious cold spot, a patch of sky where the microwave background is a little cooler than the simplest models would expect. There are hints of a slight asymmetry between one half of the sky and the other. Some large-scale modes seem oddly aligned. These features are not, on their own, smoking guns. Each could be a statistical fluke, a natural outcome of random variations in a finite sky. But taken together, they keep the door open to the possibility that our standard picture is not yet the final word. They are like smudges on the photograph, not enough to discard it, but enough to make you look twice. Scientists are careful here. The temptation to interpret every anomaly as a window into what came before the Big Bang is strong. And history is full of cases where noise was mistaken for revelation. But even when the safest explanation is chance, the very act of checking, of asking whether an odd cold spot could be the fingerprint of a pre-existing structure or a neighboring bubble, reveals how inflation has changed the kinds of questions cosmology considers legitimate. Culture feels this shift too. In science fiction, the Big Bang is rarely treated anymore as an inviolable, untouchable barrier. In films and series, from space operas to more grounded stories, you see time loops, branching timelines, multiverses, characters falling into black holes and emerging in other regions of space-time. The beginning of the universe is portrayed not as a solid wall, but as a knot that can be tied differently. Tugged at, crossed in imagination. These images are not science, but they echo what science has done. By trying to mend the cracks in the simple Big Bang picture, inflation opened a path toward a much stranger landscape, where our entire observable history might be only a local chapter in a larger, perhaps endless structure. That does not mean this picture is correct. Inflation itself, despite its successes, is not universally accepted as the only or final explanation. Some physicists worry that its flexibility makes it hard to test decisively. Others work on alternative ideas that try to address the same puzzles in different ways. The debates run through conferences and papers and long late-night conversations, but it does mean that the neat narrative of the universe began from a point, and that is all, is no longer the only serious story in town. The attempt to fix the Big Bang's internal problems has, almost accidentally, made the cosmos more baroque, not less. And in doing so, it has brought us back to a deeper, older question, now sharpened by equations and maps of the microwave sky. If even an eternally inflating universe seems to run into boundaries when you trace its history backward, if every attempt to smooth the beginning leaves some edge where our description fails, then what exactly do we mean when we ask whether the universe had a first moment at all? From here, the language we need starts to shift. Words like singularity, geodesic, and space-time boundary move from the margins of textbooks into the center of the conversation. Everyday intuition has to stretch, and sometimes snap, to follow. The moment you ask whether the universe has a first page, you discover that physics does not answer in the language of pages at all. It answers in the language of paths. In general relativity, the universe is not a box that contains things. It is the fabric of space-time itself, and everything that happens is a pattern traced within that fabric. So when physicists ask, in their careful way, whether the cosmos has a beginning, they are not picturing a fireball in the dark and wondering what came before. They are asking a narrower, stranger question They ask whether the paths that physical things can follow have an edge. Those paths have a name: geodesics. It sounds abstract, but you live on one. The orbit of the Earth around the Sun is very nearly a geodesic. An astronaut drifting freely between planets traces another. A photon leaving a distant galaxy and eventually falling into the mirror of a telescope follows a null geodesic, one of the natural paths that light prefers in curved spacetime. You can think of a geodesic as the straightest possible line available, given the geometry you are living in. On a flat sheet of paper, straight lines are familiar. On the curved surface of a sphere, the straightest paths are great circles, like the arcs traced by airplanes flying between continents. In spacetime, the straightest paths are those that a freely falling object would take if we stopped pushing on it and just let gravity do whatever gravity does. Normally, we imagine these paths as extendable without limit. If you draw an arrow on a page, you can stretch it in your mind further and further in both directions. The mathematics of geodesics often behaves the same way. You can move along them toward the future, or back toward the past, as far as you like. The equations still have something to say. But in some spacetimes, something else happens. As you follow a geodesic backward in time, you eventually reach a place where you cannot continue. The path simply stops, not because you have reached a familiar boundary, like the edge of a table, but because beyond that point, the equations cannot be extended in a way that keeps the path physical. When this occurs, physicists say the spacetime is geodesically incomplete. It has an edge, not in space, but in the way time can be traced by physical objects. This is where the technical notion of a beginning appears. In this language, asking whether the universe began is not asking, was there nothing before? It is asking, are there past-directed geodesics that cannot be extended indefinitely? If there are, then in a specific, rigorous sense, there is a past boundary, not necessarily a first moment in the storybook sense, a place where physical world lines all run into some kind of limit. The depth of this idea only really came into focus in the latter half of the 20th century, when Roger Penrose and Stephen Hawking began to explore what general relativity says about extreme situations. They were not, at first, thinking about the entire universe. They were thinking about gravitational collapse. Imagine a massive star reaching the end of its life. It runs out of nuclear fuel. Gravity takes over. The star begins to contract. If nothing stops the collapse, general relativity predicts that the star's matter will continue to fall inward. Crushing itself ever more tightly, the gravitational field becomes stronger. Space-time curvature grows. Penrose introduced the notion of a trapped surface, a region from which light itself cannot escape outward because the curvature is so intense that even outward-directed light rays are dragged inward. Using that idea, and assuming only very general conditions about the nature of matter and energy, he proved a disturbing result. Once a trapped surface forms under those conditions, some geodesics must be incomplete. Following them backward or forward, depending on the situation, you inevitably run into a boundary where the mathematics refuses to extend. In more familiar language, under realistic circumstances, gravitational collapse leads not just to something dense, but to a singularity. Hawking extended this line of thought to cosmology. Instead of looking at a collapsing star, he and his collaborators looked at an expanding universe. If the universe is expanding in a certain average sense, and if matter satisfies reasonable energy conditions, then geodesic incompleteness seems unavoidable there as well. Trace certain paths backward far enough, and they fail to extend indefinitely. There is a past edge. These results are often called singularity theorems. They were born in the study of black holes and gravitational collapse, but they quickly turned their gaze on the cosmos as a whole. They said, in effect, that under quite generic assumptions, the combination of general relativity and ordinary matter leads either to singularities in collapsing regions or to singularities when you follow expansion backward. In both cases, the same signature appears. Geodesics that cannot be continued. World lines with an end where you might have expected an infinite past. This is already an amazing fact. Before this work, it was possible to imagine that the pathologies of the simple Big Bang model might be an artifact of symmetry, or of special choices. Perhaps the singular behavior at the putative beginning was just a convenience of the coordinates used in the Friedmann-Lemaitre models. The theorems stripped away much of that hope. They did not assume perfect symmetry. They did not assume exotic matter. They set up only a small handful of physically reasonable conditions and showed that, if those hold, then some form of incompleteness is not an option. It is a consequence. But here is the subtlety that is so easy to lose in translation. The theorems do not tell you what happens at the boundary. They do not hand you a picture of a point of infinite density, nor do they whisper that everything came from nothing. They simply state that there are curves representing the possible histories of observers or particles that cannot be extended beyond a certain parameter value. The map stops. Think of an old videotape. You are watching a film, and the characters are exploring a strange house. The tension builds. They walk slowly down a hallway toward a locked door. The music draws out the moment. A hand reaches for the handle, and then the tape jams. It chews itself in the machine. The frame melts into static. You cannot watch any further, not because the story inside the fictional world necessarily ends at that door, but because your medium has given up. The film, inside its own reality, could easily continue. The characters might open the door, or turn away, or vanish. You just do not get to see it. Geodesic incompleteness is like that jammed tape. It is not a statement about the absolute end of a physical process. It is a statement about the breakdown of a particular description. Here, general relativity. At certain extremes of curvature or energy density, it tells you that something is happening which the current framework cannot follow. From the outside, looking at the equations, it can feel very final. Various quantities head toward infinity. Curvature scalars diverge. The manifold structure that underlies the theory cannot be continued smoothly. But infinity in this context is less a literal place and more a sign that the model is being pushed beyond its domain of trust. We are used to such signs in other parts of physics. A simple mathematical model of the drag on an object moving through air might predict nonsense speeds if you push the parameters beyond the range where the model was calibrated. A classical description of an atom, with electrons orbiting like planets around a miniature sun, falls apart when you try to account for radiation and stability. Those infinities and instabilities are not telling you that reality itself has blown up. They are telling you that you have reached the edge of a useful approximation. The singularity theorems are deeper and more general than those toy models, but they share this character. They say, under these broad conditions, our current theory cannot avoid running into its own limitations. Whatever lies beyond will need different tools, perhaps a quantum theory of gravity that does not yet fully exist. There is another layer to this, one that touches older human habits of mind. Long before anyone spoke of geodesics or curvature, people were already uneasy in the face of the infinite. Ancient texts often begin with some variant of a boundary statement. In the beginning, something happened. A word was spoken, a god moved, a chaos parted. What comes before is either left unspoken or described metaphorically as formlessness, void, waters, darkness, a kind of fog at the edge of imagination. These openings do not function primarily as historical accounts. They function as markers. They say, in effect, from here, our story starts. Beyond here, our language does not reach. The beginning is a narrative boundary. Modern cosmology, for all its equations, encounters its own version of this limit. It does not call it darkness on the face of the deep. It calls it geodesic incompleteness. It does not talk about the spirit moving. It talks about energy conditions and trapped surfaces. But the structure is similar. At a certain edge, the map goes dim. It is tempting, especially in popular retellings, to collapse that subtlety, to blur the distinction between our theory stops here and reality began here, to take the point at which the tape snaps and mistake it for the death of the characters. When people say the universe began with the Big Bang, they are often compressing several layers of meaning. The observational layer. There is overwhelming evidence for a hot, dense, early phase from which the cosmos has been expanding and cooling. The theoretical layer. Within general relativity, such an expanding universe, under reasonable assumptions, leads to geodesic incompleteness in the past. And then an extra, philosophical layer. Therefore, there was literally nothing before. Physics itself, at its most cautious, only fully commits to the first two layers. The third is an extrapolation, a story we tell on top of the mathematics. So when you hear a cosmologist, speaking carefully, ask whether the universe had a beginning, what they are really asking is more modest and more precise. They are asking whether the real space-time we inhabit is past complete along all physical paths, or whether there are paths that terminate in a way that cannot be removed by changing coordinates or refining the model within classical general relativity. If the answer is that some geodesics are past incomplete, then there is, in the language of the theory, a boundary. Not necessarily a first tick of a cosmic clock, but an edge to the region that the classical space-time description can cover. If the answer is that all geodesics can be extended arbitrarily far into the past, then at least within that classical framework, there is no such edge. The universe, in that mathematical sense, has no beginning, even if there are still special events, phase transitions, or changes in behavior that mark important turning points. The amazing and slightly disorienting fact is that our best theorems so far lean toward incompleteness. When you combine them with the success of the Big Bang model in describing the hot early cosmos, it becomes very natural to speak as if the beginning of that hot phase is also the beginning of everything. But as soon as you look more closely, as soon as you remember that geodesic incompleteness is a statement about the failure of a particular description, not an X drawn through reality, the question reopens. It becomes less, was there nothing before? And more, what kind of physics, if any, extends beyond the edge where general relativity fails? Does time itself dissolve there, replaced by some more primitive structure? Is there a different phase, perhaps a contracting universe that bounced, or a static regime, or something stranger that does not fit into before and after at all? Maybe there is no meaningful before in the way we use the word inside our own cosmic era. Or maybe there is, but our current instruments, both mathematical and observational, cannot yet see it. In that light, you can even reinterpret the original question that started this whole journey. Did the universe begin with the Big Bang? Might be better translated into the language of the theory as, are the geodesics that describe our observable universe past incomplete at a boundary beyond which classical general relativity has nothing to say? That is a mouthful. It does not fit neatly into headlines. It does not feel like a mythic origin line, but it has the virtue of being honest about what we actually know and about where. Even in our most successful theories, the tape starts to stutter. Once you see that the so-called beginning is really a place where our description runs out, another, quieter suspicion creeps in. What if some of those apparent endings are not telling us about the universe at all, but only about the way we chose to draw the map? Black holes are the cleanest way to feel this. In everyday language, a black hole sounds like an object, a thing in space, like a star or a planet, only stranger. In general relativity, it is more precise to say that a black hole is a region of space-time, a place where, once you cross a certain invisible surface, no future path will ever lead back out to distant observers. That surface is called the event horizon. From far away, the simplest mathematical description of a non-spinning, uncharged black hole is given by what are called Schwarzschild coordinates. You can think of them as a particular choice of grid laid over space-time. One coordinate measures something like distance from the center. Another measures time as recorded by a clock at rest infinitely far away. The usual angular coordinates wrap around, labeling directions. Write the equations in these coordinates, and something odd jumps out. As you approach the event horizon, the metric coefficients misbehave. Certain terms in the equations blow up or vanish in alarming ways. If you follow the path of an object falling inward, the description seems to say that, as seen from far away, it takes an infinite amount of time to actually reach the horizon. The object appears to freeze, ever more redshifted, fading into darkness, but never quite crossing. For a long time, this was taken at face value by many. The horizon looked like a kind of physical barrier. Not yet the central singularity, but already a place where something essential breaks. Time seems to slow and stop. The coordinates themselves whisper that you have reached a wall. Then another way of looking at the same spacetime was introduced. You can change coordinates. You can choose to label events in spacetime differently, in ways better adapted to what is physically happening. Eddington and Finkelstein, and later Martin Kruskal and George Sekeres, showed that by making a clever change of variables, you can rewrite the same Schwarzschild solution in a form where the event horizon is completely regular. No coefficients diverge there. The equations are well behaved. Geodesics pass through without any drama at all. In Eddington-Finkelstein coordinates, which are adapted to light rays falling inward, the horizon is just another light-like surface. In Kruskal-Sekeres coordinates, which go further and cover the maximal analytic extension of the solution, the entire spacetime becomes a smooth diagram in which the horizon is not a singularity. It is simply an angled line, a boundary of causal influence. The true singularity, where curvature invariants diverge and geodesics end, lies deeper within. At the center, this was a conceptual turning point. What had looked, in the original coordinates, like a genuine singularity at the horizon turned out to be a coordinate singularity. An artifact of the map, the spacetime itself, as an abstract geometric object, did not end there. It continued smoothly across. A helpful way to picture this is to think about the Earth. Draw the surface of the Earth on a flat map using the familiar system of latitude and longitude. As you approach the North Pole, the lines of longitude bunch closer together. On the map, they seem to crash into one another. The coordinate grid becomes pathological. At the exact pole, longitude is undefined. Every line of longitude meets there. If you only ever looked at that particular projection, you might think something catastrophic happens at the pole. But if you stand there, physically, nothing dramatic occurs. The surface of the Earth is smooth. You can walk around in small circles, turn on the spot, wander away. The singular behavior lies only in how the coordinates behave, not in the underlying geometry. The map breaks. The world continues. The black hole horizon, in this sense, is like the North Pole on a badly chosen map. In Schwarzschild coordinates, time appears to stop there. In Kruskal-Sekeres coordinates, the same region is perfectly ordinary, at least as far as the mathematics is concerned. The only place where the spacetime itself truly becomes singular, where no change of coordinates can cure the divergence in curvature, is at the center where the collapsing mass has been crushed. This leads to a crucial distinction. There are coordinate singularities, where what blows up is only the description. Those can be removed by choosing better coordinates. Just as you can draw a different map projection of the Earth, where the poles are treated more gently. And there are curvature singularities, where invariants built from the spacetime curvature itself go to infinity, and geodesic incompleteness appears in a way that no coordinate change can fix. Those signal a genuine breakdown of the classical theory. The amazing fact is that, for a while, physics itself struggled to tell these apart. The early language around black holes mixed the apparent freezing at the horizon with the real singularity at the center. It took careful geometric work, like Kruskal's analysis in the early 1960s, to tease them apart, to show in detail where the spacetime manifold can be extended and where it truly cannot. In that maximal extension, something even stranger appears. The full Kruskal-Sekeres diagram of the Schwarzschild solution does not just contain a black hole region and an exterior. It also contains what looks, mathematically, like a mirror image in time, a white hole, a region from which things can emerge, but into which nothing can enter. And beyond both, in the idealized picture, other asymptotically flat regions that look like separate universes, joined together by wormhole-like bridges. Are those additional regions physically real? Probably not. At least not in the way the exact, eternal Schwarzschild solution describes them. Real black holes form by collapse in a universe with matter and radiation and all kinds of complications. Those histories do not produce eternal white holes or traversable wormholes. But the very fact that the mathematics allows such extensions, that the naive singularity at the horizon evaporates in a better coordinate system, is a powerful lesson. It says, "Do not trust every infinity you see. Before you declare a boundary in space-time, ask carefully whether you are looking at the world or at a wrinkle in the chart." Now carry that lesson back to cosmology. The standard models used to describe the large-scale universe assume a huge amount of symmetry. They treat space, on average, as homogeneous and isotropic. The same in all directions, and the same at every point when you smooth over small-scale structure. Under those assumptions, the equations of general relativity reduce to a family of solutions known as the Friedmann-Lemaitre-Robertson-Walker spacetimes. In those models, the entire universe is described by a single scale factor that tells you how distances between co-moving points grow or shrink with time. Run that scale factor backward in the simplest, matter and radiation-dominated cases, and it tends to zero at a finite time in the past. Densities go to infinity. Curvature diverges. We call that limit the Big Bang singularity. But remember the Schwarzschild horizon. There, too, a particular coordinate system insisted on a singularity where none existed in the underlying geometry. Only by stepping back and asking about invariant quantities, about curvature scalars and geodesic completeness, could physicists distinguish between a coordinate artifact and a real edge. So, an uncomfortable question arises. How much of what we call the Big Bang singularity is like the black hole horizon, a result of a highly specialized choice of coordinates and symmetry assumptions? And how much of it is like the central singularity, a genuine marker of geodesic incompleteness that no clever relabeling can avoid? The singularity theorems of Penrose and Hawking do not fully answer this. They show that under broad conditions, spacetimes that expand or collapse in certain ways must contain incomplete geodesics. They tell you that singular behavior, in the sense of geodesic incompleteness, is generic. But they do not tell you its detailed form. They do not say it has to look like all of space collapsing to a point in a perfectly symmetric way. In fact, many physicists interpret those theorems not as proof that infinite densities and curvatures literally occur, but as flags planted at the border of classical general relativity. Wherever such a singular region would appear, the theory is shouting that its own assumptions are breaking. Quantum effects, or new degrees of freedom, or some deeper structure of space-time, must become relevant there. In that reading, the Big Bang singularity is more like the North Pole on a distorted cosmological map. It is a symptom of an approximation pushed beyond its domain. The true beginning, if there is one, might have a very different character. Or there might be no beginning in the usual sense, merely a boundary in our current description. You can see a soft echo of this idea in how the event horizon is treated in fiction. In the film Interstellar, when the crew approaches the black hole, the frontier does not feel like a wall. The ship does not crash into an invisible surface. The horizon is crossed. From the perspective of the falling observers, in finite, proper time, with no immediate catastrophe. Only deeper inside do things become truly strange, and the film, wisely, chooses not to pretend it can show that regime faithfully. It switches to symbolism that is actually close to what general relativity itself says. For someone freely falling into a sufficiently large black hole, the crossing of the horizon is locally uneventful. The real drama, in the classical picture, lies in the crushing approach to the central singularity. The fear, in a sense, belongs not to the boundary itself, but to the region where the theory predicts its own breakdown. Translate that back to cosmology, and a similar shift happens. The hot, dense, early phase we call the Big Bang is not necessarily the crash site. It is the horizon of our current understanding. We can cross it in our equations backward, at least partway, reconstructing what happened when the universe was denser and hotter than any star. Only when we push all the way to the idealized singular point do the equations tear. The crucial question then becomes, is that tearing telling us about the universe, or about our insistence on using a symmetric, classical, four-dimensional, purely geometric description all the way down. If it is mostly the latter, then saying the universe begins at the Big Bang might be like saying all roads end at the North Pole because your map happens to fold up there. The real geography could continue beyond in directions your current projection does not capture. To see it, you would need a different chart, perhaps drawn in the language of quantum gravity, where notions like smooth space-time and classical geodesics are not fundamental. This does not mean that the Big Bang is an illusion. The evidence for a hot, dense, early cosmos is rock solid. What it means is that the way we picture its absolute beginning might be far more a product of our tools than we often admit. Some researchers today explore cosmological models in which the Big Bang singularity is replaced by a bounce, or by a smooth transition from another phase, or by a more subtle kind of extension that only becomes visible in new variables. Others investigate whether certain coordinate choices can extend parts of the space-time beyond what the naive Friedmann-Lemaitre-Robertson-Walker description would allow, just as Kruskal extended Schwarzschild. None of these proposals is yet definitive. Each comes with its own assumptions, its own fingerprints that may or may not show up in observations. But underlying them all is the conviction that one must not confuse the failure of classical coordinates with a final metaphysical statement about reality. The amazing idea, once you let it settle, is simple and radical at the same time. The claim that the universe begins at the Big Bang may be standing on the same kind of mistake as a sailor who looks at a particular flat map, sees the lines bunching at the top, and concludes that the world must end there, in a jagged seam of paper. The deeper question, the one that will keep appearing under different disguises as this journey continues, is whether we can find a better map. One that keeps all the successes of the Big Bang picture in describing the hot early universe and the growth of structure, but that also continues past the wrinkles, showing us whether, on the other side of that apparent edge, there is more of the same, something entirely different, or a region where our ideas of before and after simply no longer apply. The moment you start to suspect that a better map might exist, you also inherit a new responsibility. You have to ask whether even the boldest new maps are really as open-ended as they seem, or whether they too run into their own edges. For a while, eternal inflation looked like a way out of the whole beginning question. If space in its inflating phase keeps stretching forever into the future, and if new bubble universes keep forming within that inflating background, perhaps there is no first one. Perhaps the story just goes on, endlessly, in both directions of time. Our own hot Big Bang would then be a local event inside a much larger, eternal structure. It is a seductive picture. No single birth, no sharp origin, just a vast sea of inflating space-time, always budding off new regions like ours. Then, in the early years of the 21st century, 3 physicists took a hard look at this idea and asked a very pointed question. Arvind Borde, Alan Guth, Alexander Vilenkin. They were not trying to disprove inflation. Guth, in fact, was one of its original architects. They were trying to understand its limits. The result they arrived at is now known as the Borde-Guth-Vilenkin theorem. It appeared in the year 2000.3. In the quiet language of mathematics, this theorem states something that, when translated, becomes one of the most unsettling facts in modern cosmology. Roughly put, the theorem says this: any universe that has been, on average, expanding along some path, cannot have that path extended indefinitely into the past. If the expansion rate, averaged along a geodesic, stays positive, then that geodesic is past incomplete. It hits a boundary. You can hear the echo of the earlier singularity theorems. Again, the language is about geodesics, about completeness, not about fireballs and mythic beginnings. But this time, the target is more specific. It is not all conceivable universes. It is those with a certain average expansion, including, in particular, the inflating models that seem to promise an escape from any talk of a beginning. The amazing part is that this conclusion does not care whether inflation goes on forever into the future. It can. It might. You can have a region where new bubble universes are spawned without end. But if the expansion along a given path has, on average, been positive, the past of that path is still finite. Somewhere behind you, no matter how far you go, the description fails. The train of geodesics does not run back without limit. A simple way to feel the intuition is with motion you do understand. Imagine a train that is speeding up, not in fits and starts, but in such a way that if you average its acceleration over a long time, the result is positive. Year after year, it gains speed. It might slow down a little on some hills, but overall, it is faster now than it was before. Now ask yourself, could that train have been accelerating like this from an infinitely distant past? If the acceleration is truly positive on average, the answer is no. If you follow its history backward, there comes a point where the story, "This train has been gaining speed," breaks. Because speeds cannot drop below zero, there is a limit to how far back you can stretch that description. Beyond some moment, the idea of it having been slower and slower forever no longer makes sense. The Borda-Guth-Vilenkin theorem does something analogous in space-time. Replace the train with a geodesic, and its speed with the local expansion rate. If the universe is, on average, expanding along that path, you cannot stretch that expansion story forever into the past. Somewhere, the line of events ends, not necessarily in a classical singularity of the simple Big Bang type, but in a boundary where the expansion model ceases to apply. When this result first appeared, it landed in a landscape where many cosmologists hoped that eternal inflation would, in some sense, remove the need to talk about any sort of beginning at all. After all, if you have a mechanism that naturally produces an infinite hierarchy of universes into the future, it is very tempting to suppose that it has always been doing so, that the inflating background is past eternal. The theorem said, not so fast. It does not say that a classical Big Bang, as usually portrayed, definitely happened. It does not insist that there is a literal first, second, or a single cosmic fireball. What it does say is more modest and more sharp. It says that if you try to describe the past purely with models in which the universe has a positive average expansion rate, then at some point, those models must fail. There is a past boundary to that regime. In other words, eternal inflation, by itself, cannot give you an eternally inflating past. This revived an old tension in a new form. Some took the theorem as strong evidence that the universe, in some real sense, must have had a beginning. Not necessarily a Big Bang in the classic picture, but some kind of initial event, a first chapter that is qualitatively different from what comes after. Others reacted differently. They pointed out that the theorem rests on particular assumptions. It speaks about average expansion along geodesics. It uses classical notions of space-time. It assumes certain energy conditions. Perhaps, they suggested, you could avoid its conclusion by having a pre-inflationary phase that is not expanding on average. A contracting phase, for instance, that bounces. Or a static, emergent phase that sits for an immense duration before inflation switches on. In those scenarios, the Borda-Guth-Vilenkin result still applies to the inflating phase, but that phase no longer extends all the way back. There is something else before it. Perhaps a contracting cosmos that shrinks, reaches a high density, and then transitions into expansion. Perhaps a quantum gravitational state that does not have a simple space-time geometry at all. The fork in the road is clear. On one side, you accept that some kind of beginning exists. You take the past incompleteness of geodesics in expanding regions as indicating that there was a first something, even if its nature is unknown. You may then look for hints, in quantum cosmology or in deeper theories, about what that initial something might look like. On the other side, you insist that the past continues, but not in the form of a merely expanding universe. You imagine phases where the average expansion rate is zero, or negative, or undefined. You may build models of cyclic universes that pass through alternating periods of contraction and expansion, or emergent universes that asymptotically approach a quasi-static state in the remote past. In both branches, the theorem plays the same role. It is a constraint. It says, If you want a universe with no past boundary at all, you cannot describe its entire history using only expanding phases like the ones we currently observe. Somewhere, the physics must be different. Somewhere, the language of space expanding must give way to something else. There is a philosophical resonance here that is hard to ignore. Long before modern cosmology, Immanuel Kant grappled with what he called antinomies of pure reason. One of them concerned time and the cosmos. He argued that if you reason a certain way, you can convince yourself that the world must have had a beginning in time. If you reason another way, you can convince yourself that it cannot have had a beginning, that time must stretch without limit. Both chains of reasoning, he thought, were internally persuasive, yet mutually incompatible, revealing the limits of trying to apply certain kinds of thought to the universe as a whole. In a way, the Borda-Guth-Vilenkin theorem recasts that old tension in the language of geodesics and expansion rates. It does not decide the metaphysical question of whether the universe truly began or not, but it tells you that if you want to imagine a cosmos that has always looked roughly like the expanding one we inhabit, you will run into mathematical trouble. Your geodesics will be past incomplete. If you still want a truly past eternal universe, you are pushed into more exotic territory. You need to posit phases that look very different from what we see now. Perhaps you accept a pre-Big Bang contraction that erases earlier information in a bounce. Perhaps you picture a beginningless, timeless quantum state that, at some point, gives rise to classical spacetime in a way not captured by any geodesic. The theorem itself does not care which route you take. It just quietly closes some doors and leaves others open. There is another important nuance worth holding on to. When cosmologists talk about an edge to the past in this context, they do not mean a brick wall. They mean a place where a particular kind of description stops working. If you are in an inflating region, or in a bubble universe like ours that emerged from such a region, and you trace your world line backward, there will be a finite amount of proper time before you hit a boundary in the classical, expanding picture. That is what past incompleteness means here. What lies beyond that boundary could be many things. A different space-time phase, a quantum gravitational regime where geodesics are not even the right language, a domain where time itself is not defined in the way we currently understand it, or perhaps nothing at all in any sense that connects to our physics. From the point of view of someone lying awake at night, staring into the dark and thinking about beginnings, this may feel unsatisfying. You ask, did the universe begin? And physics replies, if by universe you mean a classical space-time with average expansion like the one we observe, then along your path, that description cannot be extended forever into the past. It is a precise answer to a narrower question than the one the human mind likes to ask. Yet there is a kind of quiet honesty in that narrowness. Instead of promising a clean origin story, the Borda-Guth-Vilenkin theorem does something else. It tells you that even the grandest picture we have drawn so far, with eternal inflation and infinite bubble universes, is not infinite in every direction, that the same pattern keeps repeating. Follow the trail of geodesics back far enough, and they fade into a region where our familiar concepts fail. You can see how this might change the emotional tone of the Big Bang idea without changing any of the observations that support it. If you once believed that eternal inflation gave you a universe that had simply always been there, with no need for any sort of first anything, the theorem takes that away. It says that somewhere, in the deep past, your inflating background itself must give way. That there is still, in a technical but real sense, a past boundary. If you were inclined, for philosophical or personal reasons, to believe that the universe must have had a beginning, the theorem can feel like support. Not proof of your preferred picture, but a sign that contemporary cosmology does not easily accommodate a fully past eternal expansion. If you are content with uncertainty, the theorem is a reminder of scale. We have managed to push our understanding back across billions of years of cosmic history, reconstructing a rich narrative from faint microwaves and the motions of galaxies. We have even begun to probe the physics of the first fractions of a second after the onset of hot expansion. Yet when we reach for the question of whether there was before, we still run into structures in the mathematics that say, from here on, the physics must change. And so, the Borda-Guth-Vilenkin result does something that very few pieces of modern science manage to do so directly. It brings us back to a feeling that is both ancient and sharply contemporary. We stand inside a universe that is expanding. We have good evidence that this expansion has been going on for a long time. We have models that may describe phases of ultra-rapid growth, and even mechanisms by which regions like ours can bud off from a larger inflating spacetime. But when we try to stretch that story of expansion into an infinite past, the theory itself grows thin and transparent, until our paths reach a place where, once again, the map goes dim. Even the idea designed to stretch the Big Bang into a wider, endless sea is itself pushed up against an edge. Beyond that edge, by definition, the physics must be different. Whether that difference means a genuine beginning, or an earlier phase that does not resemble our expanding cosmos at all, remains open. But the mere fact that the question refuses to go away, even in the most ambitious cosmological schemes, is perhaps the most haunting part of all. Once you know that even an endless expansion can carry a hidden edge in its past, the picture of a single, sharp beginning feels less solid. The mind starts to play with another possibility. Maybe what we call the beginning is not a cliff, but a bend in a much longer road. In the standard classroom sketch, the universe is drawn with a simple history. The scale factor grows monotonically from zero. There is an initial singular point, then expansion, then the cooling and structure and chemistry that eventually lead to us. It is a clean arc. It is also only one of many ways space-time can, in principle, behave. If you loosen the assumptions a little, the equations of general relativity, especially once you start to imagine how quantum effects might join in, allow for more intricate scripts, histories in which there is no explosion from literal zero, only transitions from one phase to another. One of the simplest to picture is a bouncing universe. Imagine, instead of running time backward to a point where everything collapses into an impossible density, you keep going and find that the expansion turns around. Galaxies do not recede forever. They begin to move toward one another. The scale factor shrinks. The cosmos enters a phase of contraction. As the universe contracts, densities rise. Temperatures soar. Structures that once stood apart are pressed closer together. If gravity were the only actor, and if classical general relativity held all the way down, this would end badly, in a crushing singularity that looks suspiciously like the one we were trying to avoid. But now imagine that, at some extreme density, new physics activates. Quantum properties of spacetime itself begin to matter. Instead of allowing curvature to grow without bound, these effects push back, providing a kind of repulsive component that counters the collapse. The contraction slows, it halts, then it reverses. From the inside, viewed by observers who live through it, the moment of reversal could look very much like a Big Bang. Temperatures are enormous. Matter is in exotic states. Expansion is rapid, yet, in this picture, it is not the birth of everything. It is a turning point, a bounce. Before our expanding phase, there was a contracting one. The history does not terminate at a 0 point. It bends. This sort of scenario appears in several guises. In some approaches, quantum corrections to the Friedmann equations, inspired by attempts to quantize gravity, naturally produce terms that act like negative effective energy density at extremely high curvature, generating a bounce. In others, special kinds of matter with unusual pressure properties are invoked to arrest collapse before singularity is reached. These models do not come for free. To make them work, you often have to give up classical energy conditions that, in more ordinary regimes, express the idea that energy density, as measured by any observer, is non-negative, and that gravity is, on the whole, attractive. Bounces tend to require, somewhere, a violation of those conditions. Matter and energy must behave in ways that have no direct counterpart in everyday physics. That does not make them impossible. Quantum fields in curved space-time already show that, over small regions and short times, effective energy densities can dip below zero. The Casimir effect, for example, is a laboratory manifestation of such behavior. But it does mean that non-singular bouncing cosmologies are not simply the straightforward continuation of the matter and forces we are used to. They require something strange. A different family of ideas explores the opposite end of the dynamical spectrum. Not contraction, but an extended near stillness. In these emergent or static then expanding scenarios, the universe spends an immense time in a quasi-steady state. Space is not dramatically expanding or contracting on the largest scales. It is in a delicate balance, perhaps supported by some sort of vacuum energy or by a mixture of fields that lock the expansion rate near zero. During this long, quiet era, the cosmos can, in principle, exist forever. Quantum fluctuations come and go. Fields jitter. Nothing globally dramatic happens. There is no singular beginning here, only a perpetual present. Then, at some point, the balance tips. A phase transition occurs. A field that once sat in a high-energy plateau rolls down. The effective cosmological constant changes sign or magnitude. Inflation ignites. Space starts to expand rapidly, then eventually hands over to the more familiar, slower expansion of the Big Bang model. To observers living after that transition, looking back with telescopes and equations, it might appear as if everything began in the fiery onset of expansion. The earlier static phase would leave little obvious imprint. The Big Bang would again be a kind of horizon of accessible history, not necessarily the true start. These constructions, too, come with costs. The static phase has to be stable for an enormous duration, and yet susceptible eventually to a graceful exit. The transition must seed the right kind of fluctuations. The model has to thread a needle between theoretical consistency and observational constraint. Still, the very fact that such possibilities exist within the mathematical space of cosmology is striking. They show that the naive association of hot, dense, early universe with absolute beginning is, at the level of equations, not compulsory. In recent years, cosmologists have gone further and tried to make this intuition precise. They ask detailed questions about which specific inflationary histories contain genuine curvature singularities and which, at least in an idealized mathematical sense, can be smoothly extended beyond the point where the simplest Friedmann-Lemaitre-Robertson-Walker description would say, "Here is the bang." The logic is subtle. Given an inflationary model specified by some field or fields, and a potential that governs their dynamics, you can often solve the equations back in time and ask what happens as you approach the would-be initial singularity. In some cases, curvature invariants grow without bound, and geodesics are incomplete in a way that no change of coordinates can cure. In others, the behavior, while extreme, remains finite. The space-time can be continued beyond that region in a larger extension. In technical papers and seminars, this becomes a taxonomy. This class of models is singular in the strong sense. That class is only geodesically incomplete in the restricted symmetry ansatz, but can be extended in more general geometries. This other class is fully non-singular within a modified gravity framework that enforces a maximum curvature. Outside that circle of experts, the story arrived in a different costume. Headlines and popular articles spoke of glimpsing past the Big Bang, as if telescopes had somehow peered through an origin wall and photographed what lay on the far side. What actually happened in those discussions was quieter and more abstract. No one saw a pre-Big Bang epoch directly. What they did was show, with pencil and paper and sometimes numerical simulations, that the same equations which describe our inflationary past can, in some scenarios, be smoothly attached to earlier phases. That the apparent singularity at the beginning of time in those models is, in such cases, more like the horizon of a coordinate chart than a literal end. Again, there is a price. Many non-singular histories, whether bouncing or emergent or limiting curvature, require violations of those classic energy conditions. They demand matter with pressures so negative that gravity becomes repulsive at high densities, or modifications of the Einstein equations that cap curvature at some large but finite value. This is the spirit behind limiting curvature ideas. Instead of allowing space-time to be compressed into arbitrarily sharp peaks of curvature, these proposals build in a rule that says, beyond a certain threshold, the effective response of gravity softens. The closer you try to push the geometry toward a singular configuration, the stronger the counteracting effect becomes, until the universe, instead of producing an infinite spike, folds into a bounce or a smooth transition. An everyday image might help. Imagine driving on a foggy mountain road at night. Your headlights reach only so far. Ahead, the strip of asphalt runs smoothly and then appears to vanish into the mist at what looks, from the driver's seat, like a sheer drop. Your stomach tightens. You lift your foot from the accelerator. As you approach, you realize that the road does not end. It turns sharply away, hugging the side of the mountain. The apparent cliff was an illusion, created by limited visibility and the way the light fell. There was no physical edge there, only a bend hiding beyond your sight. In this metaphor, the simple Big Bang picture is like what you see from a distance, a straight road running into nothing. The more elaborate cosmological models that include bounces or emergent phases are like the revelation, as you get closer, that the road bends and continues. The fog is our limited theoretical and observational reach. We cannot, at least not yet, access the regimes where curvature approaches its would-be maximum, either with experiments on Earth or with direct astronomical data. We are extrapolating. We are trusting that certain modified equations capture what happens in conditions we have never encountered. That is why, in the end, these non-singular histories remain possibilities rather than confirmed descriptions. They must answer to the same judge as any cosmological model: the sky. Does the spectrum of primordial fluctuations they produce match what we see in the cosmic microwave background and large-scale structure? Do they predict relics that have not been observed? Could they, one day, be distinguished by the pattern of primordial gravitational waves, or by subtle imprints on how structures form? Those questions are still open. For now, what matters for our quiet journey through the idea of a universe that may not start with the Big Bang is something simpler. Inside the mathematics of cosmology, there are consistent histories in which there is no literal zero point for the scale factor. No moment at which space goes from non-existence to existence in a single jump. Only regions where the behavior of space-time changes character, from contraction to expansion, from stasis to inflation, from one phase of order to another. Seen from that angle, the phrase Big Bang becomes less the name of an absolute origin and more the label we give to the boundary between parts of our map. It is the zone where simple, symmetric models blow up, where our usual extrapolations stop making sense, where new physics must step in. The amazing and somewhat humbling lesson is that there may be no single privileged time slice you could point to and say, in any final sense, this is where everything began. There might only be a sequence of transitions, each one the beginning of something and the end of something else, and our own cosmic era just happens to sit close to one of those bends. From within our short lives, looking back across a few billions of years of light, it is natural to compress all that complexity into a single word: bang. But as the models grow richer, that word starts to feel less like a complete story and more like a placeholder, a sign at the edge of the known, warning not that there is nothing beyond, but that beyond this point, the path we have been following no longer shows us the whole road. Once you start seeing the Big Bang as a bend in the road instead of a cliff, another question arrives almost automatically. What if the road itself is only a lit strip on a much larger surface, and the darkness around it is not emptiness, but the rest of a world your coordinates simply do not reach? In the language of cosmology, that lit strip is the familiar description we use for our universe today. On the largest scales, everything we see is well described by a family of models called Friedmann-Lemaitre-Robertson-Walker spacetimes. In those models, the universe is, on average, homogeneous and isotropic. That means that if you smooth over individual galaxies and clusters, the cosmos looks roughly the same in every direction and at every point. Space expands with time, but it does so in a way that preserves this large-scale uniformity. That simple picture fits our observations remarkably well. The cosmic microwave background is almost the same temperature everywhere. Galaxy surveys show that, beyond a certain scale, matter distribution becomes statistically uniform. When we plug those facts into Einstein's equations, we get an expanding Friedmann-Lemaitre-Robertson-Walker universe with a specific mix of matter, radiation, and something else. That something else is an ingredient that behaves like vacuum energy. It has negative pressure. It does not clump like ordinary matter. In the equations, it acts very much like a cosmological constant, the same kind of term Einstein once introduced, then abandoned, and that cosmologists later revived to explain why the universe's expansion is accelerating. Here is the amazing twist. When that vacuum energy-like component dominates, the Friedmann-Lemaitre-Robertson-Walker universe begins to resemble a special space-time called de Sitter space. De Sitter space is a solution to Einstein's equations with only a positive cosmological constant and no ordinary matter or radiation. It is, in a sense, the purest form of a universe driven only by vacuum energy. Mathematically, it is highly symmetric, the same everywhere, the same everywhen. If you choose the right coordinates, you can imagine it as a kind of four-dimensional analog of a sphere, not in space, but in space-time. We, living inside our expanding patch, do not see that whole structure. We use coordinates that are adapted to a particular way of slicing de Sitter space into spatial sections that expand with time. Those coordinates only cover a portion of the full manifold, the way a map of one hemisphere covers only part of the Earth. In those coordinates, there appears to be a past boundary. If you trace the scale factor backward, it shrinks. And at a finite time in the past, it seems to vanish. Looked at through that narrow chart, you might say, here, the universe begins. But step back. Adopt the full de Sitter view, and you realize something else. That apparent beginning was a coordinate horizon, not a physical edge. The space-time continues beyond it. There are other regions, other slices. The boundary is like the edge of your map at high latitude, not the edge of the world. If our universe were exactly a de Sitter space-time, or exactly a Friedmann-Lemaitre-Robertson-Walker patch with pure vacuum energy dominating all the way back, then there would be a precise sense in which the Big Bang singularity we draw in our usual coordinates could be a map artifact, a wrinkle of the chart. In that special case, the beginning might be something like the North Pole on a distorted projection. Your coordinates break down there. Your lines of constant time all converge, but the underlying geometry is smooth and continues beyond. The past boundary is not a brick wall. It is the place where your chosen chart runs out of room. This is a striking idea. It suggests that, at least in principle, some cosmological past boundaries might be like black hole horizons in Schwarzschild coordinates. Artifacts of our perspective, removable by embedding our patch into a larger spacetime. But there is a catch, and it is a delicate one. For the extension into a larger de Sitter space to be smooth, the region near the would-be boundary has to be almost perfectly dominated by vacuum energy. That means not only that ordinary matter and radiation are negligible, but that any inhomogeneities, any lumps and ripples in the energy density, must be vanishingly small. The spacetime near that surface has to be extremely, almost unimaginably, smooth. Our universe, however, is not perfectly smooth, and we know this not from theory, but from the sky itself. The cosmic microwave background, for all its calm uniformity, is dappled with tiny temperature fluctuations. On the sky, you can picture them as faint blotches, slightly warmer and slightly cooler spots. The amplitude of those variations is small, roughly 1 part in 100,000. If you did not look carefully, you might call it featureless. But those little wrinkles are real, and they matter. They are the seeds from which all later structure grew. Over billions of years, gravity amplified them. Slightly denser regions pulled in more matter, becoming galaxies, Clusters, filaments, slightly emptier regions became cosmic voids. Without those primordial inhomogeneities, the universe would be a bland soup, perhaps too featureless for stars and planets and living beings to emerge. From the point of view of a de Sitter extension, though, those same ripples are trouble. They mean that near the would-be boundary, the universe is not perfectly dominated by vacuum energy. There is a small, but non-zero, contribution from inhomogeneous matter and radiation. The geometry is not exactly the ideal, maximally symmetric de Sitter form. Mathematically, this can spoil the smoothness of the extension. Those tiny lumps can bend space-time just enough to turn what looked, in the idealized model, like a coordinate horizon into a true curvature singularity. Instead of gliding harmlessly across a de Sitter boundary in a larger manifold, your geodesics might genuinely end there. The difference between an artifact and an edge can hinge on the presence of those faint wrinkles. Precision measurements of the cosmic microwave background let us quantify those wrinkles. The Planck satellite, and other observatories before and after it, have mapped the pattern of temperature fluctuations across the sky at fine angular resolution. They give us a detailed portrait of the primordial inhomogeneities. Those data tell us that the universe is extremely close to homogeneous on large scales, but not perfectly so. The deviations are small, but they follow a very specific spectrum. Any attempt to treat our past boundary as a simple de Sitter coordinate horizon has to contend with that fact. It has to show how those real, measured lumps can be compatible with a smooth extension. This turns the simple, hopeful picture of our universe is just a de Sitter patch into something more precarious. The idea is not ruled out, but it becomes fragile. It depends on the precise way in which vacuum energy dominates near the boundary, and on whether the inhomogeneities we see can be made to fade away or remain controlled in whatever larger spacetime one proposes. An image might help to hold this in your mind. Imagine de Sitter space as a vast, dark ocean, smooth, featureless, stretching far beyond anything you can directly explore. Our observable universe, as described by a Friedmann-Lemaitre-Robertson-Walker model with matter, radiation, and dark energy, is like a beam of light playing on the surface of that water. Within that beam, you see waves and ripples, small patterns, the foam of galaxies, the afterglow of the Big Bang. Outside the beam, everything is dark to you. You do not know whether the water continues calmly, whether there is a shoreline, or whether the ocean falls off into something else entirely. When you trace the history of that illuminated patch backward, the light grows dimmer. The region you can see shrinks. Eventually, at what we call the Big Bang in our coordinates, the beam seems to end in darkness. The question is that darkness the actual shore of the sea, where the water literally stops? Or is it simply the limit of your torch, a place where your current way of shining light cannot reach, but where the ocean itself goes on? Treating the Big Bang as a coordinate artifact in de Sitter space is like assuming it is just the limit of the flashlight. There is more ocean beyond, but your chosen coordinates cannot see it. Treating it as a true curvature singularity is like declaring that the darkness hides a cliff, a place where the water stops existing. The mathematics of general relativity, combined with certain assumptions about dark energy, does allow the first kind of picture in special cases. There are solutions in which our expanding Friedmann-Lemaitre-Robertson-Walker universe with vacuum energy can be embedded into a larger de Sitter manifold, and the Big Bang surface becomes a mere coordinate horizon. But the same mathematics, when you add realistic inhomogeneities of the sort we infer from the cosmic microwave background, often pushes you back toward the second picture. The ripples in the beam may be enough to ruin the simple, smooth match with the larger ocean. The would-be extension develops singular structure. The shore may be real after all. At this point, the story becomes less about what is definitely true and more about how sensitive our conclusions are to the details of the earliest universe. How smooth was it, really, near the edge of our past light cone? How dominant was vacuum energy-like behavior? How robust is any proposed de Sitter extension to small departures from perfect symmetry? These might sound like questions only a specialist could love, but notice what they do to the larger theme. They tell us that even the possibility of the Big Bang being just a coordinate illusion is not an all-or-nothing claim about reality. It is a conditional statement. If the early universe was smooth in a particular, very strict sense, if vacuum energy fully controlled the dynamics near the boundary, then the Big Bang in our coordinates might be like the North Pole on a map of de Sitter space. If, on the other hand, even tiny primordial wrinkles persist in a way that cannot be ironed out, then that trick does not work. The Big Bang remains, in the language of the theory, a real singular edge. In either case, the role of observations is central. The cosmic microwave background, the distribution of galaxies, the way structures grew over time. These are not just pretty pictures. They are the constraints that decide whether a given mathematical extension is plausible. The wrinkles in the sky are not mere noise. They are part of the decision about whether our past boundary is a map illusion or a physical limit. So we arrive at a strangely balanced conclusion. The equations of general relativity are generous enough to allow cosmological histories in which the Big Bang singularity, as written in simple Friedmann-Lemaitre-Robertson-Walker coordinates, is not the ultimate edge. In those stories, our universe is a patch of a larger de Sitter-like spacetime, and the place where our chart goes bad is more like a horizon than a birth. At the same time, the real universe we inhabit is laced with small, measurable imperfections. Those imperfections are the reason anything interesting exists. They may also be the reason our past cannot be smoothed into a larger de Sitter sea without running into genuine singular behavior. Whether the Big Bang is, in the end, more like the seam of a map or more like the end of the road depends sensitively on how wrinkled the earliest universe truly was. And that, for now, is one of the most quietly astonishing facts of all. The ultimate question of whether our cosmos began as a coordinate mirage or a real singular event may hinge on those faint, almost invisible blotches of warmth and cold scattered across the microwave sky like grain in an old photograph. If the wrinkles in the earliest universe decide whether our maps can be smoothly extended, there is a deeper question hiding underneath them. What if, before the geometry can tear, the very rules that govern it quietly change? Up to this point, most of the story has been told in the language of general relativity, smooth spacetime, curvature, geodesics, energy conditions. In that language, singularity theorems are like warning signs. Follow gravity far enough into collapse, or follow expansion far enough back, and the equations drive you toward infinite curvature, infinite density, incomplete paths. The tape snaps, but those theorems come with a silent clause. They are theorems about classical physics. They assume that space-time can be treated as a smooth continuum all the way down, and that gravity is described by Einstein's equations alone. At some point, that assumption has to fail. The question is not whether it fails, but how. Quantum mechanics already taught us that matter does not like to be squeezed without limit. Electrons in an atom do not spiral into the nucleus. Instead, the rules of the microscopic world force them into specific orbitals with energies that cannot drop arbitrarily low. In dense stars, the same quantum pressure, acting on electrons or on neutrons, can resist the pull of gravity up to a point, holding white dwarfs and neutron stars in equilibrium. Many ideas in quantum gravity are, in spirit, attempts to extend that pattern from matter into space-time itself. Instead of particles refusing to occupy the same state, you imagine space-time refusing to be bent beyond a certain tightness. Instead of quantum mechanics preventing an atom from collapsing, quantum gravity might prevent the universe from crushing into an actual point. At extreme densities, the very fabric of geometry could push back. The detailed proposals vary, but the broad theme is surprisingly consistent. In a wide class of quantum gravity-inspired models, what looks like a Big Bang singularity in classical general relativity is replaced by something softer. A bounce. Curvature rises as you go back in time, but only up to a maximum finite value. Then the behavior reverses. The collapsing phase hands off to an expanding phase. The crunch becomes a bridge. In some approaches, space-time is not fundamentally smooth at all. Loop quantum gravity, for instance, suggests that geometric quantities, like area and volume, come in discrete units, the way energy levels in an atom do. When cosmologists take those ideas and apply them to the very early universe, they find that as you approach the would-be singularity, new quantum terms appear in the effective equations. Those terms act repulsively at extremely high densities, generating a bounce. The picture that emerges in such loop quantum cosmology models is both simple and unsettling. Our expanding universe was preceded by a contracting one. The Big Bang is not the first moment of time. It is the turning point where the contraction, slowed and reversed by quantum geometry effects, becomes expansion. Other frameworks aim for a similar outcome by different routes. Limiting curvature ideas, which we touched on before, build into the theory a maximum allowed curvature. As the universe contracts and curvature grows, approaching that ceiling, the effective dynamics change. Gravity softens. The pressure coming from quantum corrections or modified gravity terms stands in for the classical attractive pull, and the cosmos rebounds instead of tearing. String theory and related higher dimensional pictures add yet another twist. In some of those scenarios, our observable universe is a three-dimensional brane, embedded in a higher dimensional space. The Big Bang, in that view, can be interpreted as a collision between branes or as a transition inside a larger, more complex structure. In the so-called ekpyrotic and cyclic models, two branes approach, interact, and separate repeatedly over vast stretches of time. Each close encounter produces a hot, dense phase that, from the point of view of observers living on a brane, looks like a bang, but there is no absolute beginning. The collisions are chapters in an ongoing story inside a higher dimensional stage. There are also proposals where the Big Bang is not a sharp bounce at all, but a smooth rounding of space-time. In the no-boundary idea associated with James Hartle and Stephen Hawking, for example, the early universe is described by a geometry in which time, near the apparent origin, behaves more like a spatial direction. Instead of a singular point, there is a finite, smooth cap. Asking what happened before becomes as meaningless as asking what lies north of the North Pole on a globe, not because there is a wall, but because the coordinates that defined before simply fade out. Across all of these approaches, you can feel the same structural metaphor. General relativity, when pushed into regimes of enormous curvature, predicts that the bridge of space-time will snap under infinite load. Quantum gravity, whatever its final form, seems to prefer another outcome. The material of the bridge changes near the limit. It bends. It creaks. It may deform beyond recognition, but instead of shattering into a mathematical infinity, it reforms on the other side. From a distance, using only classical tools, that reorganized region looks like a singularity, a place where the theory breaks down. From the inside, once you upgrade the description to include quantum effects, it could be a passage. Of course, saying this in words is much easier than turning it into a complete, predictive theory. Quantum gravity is one of the most unfinished parts of physics. We do not yet have a single agreed-upon framework that unifies general relativity and quantum mechanics in a way that can be tested everywhere. The models we can write down are often simplified, restricted to high symmetry cases, or built on speculative ingredients. They may capture only a piece of the full dynamics. They sometimes rely on approximations whose validity is hard to check. Their parameters can be tuned. Their connection to a fundamental theory can be tenuous. Yet it is important to see them for what they are trying to do. They are not merely flights of fancy. They are responses to a very specific challenge thrown down by the singularity theorems. Those theorems say, loud and clear, if you insist on treating space-time as a classical manifold obeying Einstein's equations, you will run into incomplete geodesics. You will meet infinities. Beyond that point, your description is self-contradictory. The quantum gravity-inspired models answer, then we will not insist. We will change the rules before the contradictions arrive. From an observational point of view, this matters because different histories leave different fingerprints on the cosmos we can see. A universe that emerges from a sharp, classical Big Bang, driven immediately into inflation, will imprint one kind of pattern on the cosmic microwave background, particularly in how quantum fluctuations are stretched into large-scale density variations and in how gravitational waves are generated. A universe that passes through a bounce, or that spends time in a pre-bang contracting phase with its own dynamics, may leave a different pattern. The timing and shape of the bounce, the way quantum corrections modify the effective stress energy, the presence or absence of certain kinds of anisotropies, all of these can, in principle, influence the spectrum of primordial gravitational waves, the fine details of temperature and polarization in the microwave sky, and the distribution of structures at large scales. This is why experiments that hunt for subtle signatures in the polarization of the cosmic microwave background, especially the twisting patterns known as B-modes, are so important. A detection of a particular primordial gravitational wave background could support a simple inflationary origin. A different pattern, or a surprising absence, might point to more exotic pasts. At the moment, the data are not sharp enough to pick one quantum cosmological script over all the others. What they do say is that any viable model, whether bouncing or not, must reproduce the well-measured statistics of the sky we already see. That is a high bar. Many ideas fall away under that constraint. Others survive and wait for more precise tests. It is also crucial to be honest about the status of these models. They are not established facts. They live in the realm of candidate theories. Some are better grounded than others. Some may turn out to be mathematical mirages. Interesting, but not realized in nature. Others might be approximations to a deeper framework we have not yet fully written down. The amazing fact, for our purposes, is not that quantum gravity has already replaced the Big Bang with a bounce. It is that, when physicists take seriously the idea that general relativity must give way at extreme curvature, many of the consistent, mathematically controlled ways to do so naturally soften the singularity. They do not double down on infinity. They create bridges. This changes the emotional color of the question we began with. If your picture of the universe's origin is a hard explosion from absolute nothingness, you might feel that you are staring at a wall. There is a single, bright flash, and before it, a void that physics cannot touch. Meaning flows from the mystery of that instant, or not at all. If, instead, your picture is of a quantum bridge between phases, or of an endless chain of transitions inside a larger structure, the mood is different. The universe still has edges in our descriptions. There are still boundaries where one regime ends and another begins. But the stark contrast between something and nothing softens. You are no longer forced to imagine existence squeezed into a single magic moment. You can imagine that what looks, from here, like a beginning, is the way a new pattern of space-time and matter emerges from an older one, under rules that change but do not vanish. General relativity, on its own, tells you how far space-time can stretch before its classical approximations fail. It charts the terrain up to the edge of its own reliability and labels the rest with a cautious singularity. Quantum gravity, whatever precise form it eventually takes, is our attempt to peer beyond that label, not by leaping into myth, but by asking how the fabric itself might be woven to avoid the infinite tiers the classical theory predicts. In that sense, the gentle bounces and rounded caps and higher dimensional collisions are not really answers to the question, what was there before the Big Bang? They are ways of rewriting the question. They suggest that the true frontier might not lie between nothing and something, but between one kind of something and another, separated by a region where our current language for space and time has to learn new grammar. To get a feeling for that new grammar, it helps to slow the picture down in your mind until the whole universe feels small enough to hold. Imagine taking the expansion history of the cosmos and playing it like a film on a screen you can approach. You walk toward the opening frames. Galaxies dissolve into a smooth glow. At earlier times, even those glows blur into a hot, nearly uniform plasma. Keep moving, and the temperatures in the story climb beyond what any collider on Earth can probe. Particles and fields merge into more primitive degrees of freedom. In the classical script, you keep compressing until the frame itself cracks. The theory writes an infinity and falls silent. Quantum gravity says, pause right before that crack. At those extreme densities, the idea of space-time as a perfectly smooth sheet is probably wrong. Many approaches suggest that, on the smallest scales, geometry is grainy, not grainy like sand, with tiny hard grains that you could in principle isolate, but grainy in a softer, statistical way. There is a minimum area that makes sense to talk about, a minimum volume. You cannot simply squeeze geometry into an arbitrarily small region without changing its nature. In such a world, trying to push space-time into a classical singularity is like trying to compress water into a grain of dust. The usual description just stops matching the stuff you are dealing with. One way people visualize this is as a kind of space-time foam. On scales far smaller than any atom, quantum fluctuations in geometry make distances and durations wobble. At ordinary energies, these fluctuations average out into the smooth space-time we experience. At energies near the would-be singularity, they become the main actors. The foam is no longer a gentle background noise. It is the stage itself. If you take that seriously and feed it into simplified cosmological equations, a pattern often appears. The effective energy associated with quantum geometry behaves strangely. In some models, as the density increases, this quantum contribution becomes negative in just the right way to counteract further collapse. The universe, instead of smashing into an unreachable state, slows, hovers at a maximum curvature, and then expands again. You can think of it as a cosmic version of the degeneracy pressure that holds up a white dwarf. In that star, quantum rules prevent electrons from being squeezed into the same quantum state, creating a repulsive pressure that counters gravity up to a point. In a quantum universe, near a would-be Big Bang, the discrete nature of geometry itself creates a kind of resistance to being bent beyond a certain sharpness. Of course, this is still metaphor. Underneath it lie equations, operators, Hilbert spaces, and all the technical machinery of quantum theory, but the story they suggest is not an explosion from absolute zero. It is a system that, when pushed to its limits, changes its response, rather than allowing a literal infinity. Higher dimensional scenarios add another layer of strangeness. In some string-inspired pictures, what we think of as fundamental particles are vibrations of tiny extended objects, strings and brains, moving in more than 3 spatial dimensions. The geometry of those extra dimensions affects the physics we see. The early universe, in that context, might have been shaped not only by what happens in our familiar 3 dimensions of space, but by the shape and motion of dimensions we cannot directly perceive. In certain brain world models, our observable universe lives on a 3-dimensional membrane embedded in a higher dimensional bulk. The Big Bang, then, can be reimagined as an interaction between brains in that larger space. 2 brains approach, collide, and rebound. The collision dumps energy into matter and radiation on the brains. To an observer made of that matter, this looks like a hot beginning. To someone who could see the whole bulk, it would be an event within an ongoing higher dimensional dance. Whether that dance is cyclic, repeating over and over, or a one-time encounter, is a question those models answer in different ways. What unites them is the insistence that the Big Bang is not a creation ex nihilo, but a structural transition inside a larger, pre-existing framework. All of this can feel very far from anything you can test. Yet the thread back to observation is not entirely broken. The early universe, however exotic, had to evolve into the one we see. It had to produce the nearly scale-invariant spectrum of primordial fluctuations written into the cosmic microwave background. It had to seed the growth of galaxies and clusters. It had to avoid leaving behind huge relics that would have been obvious in our telescopes. Bouncing models, brain collision scenarios, and limiting curvature frameworks all have to confront this. They need to show not only that they avoid singularities, but that they can reproduce the successful predictions of more conventional inflationary cosmology, or, where they depart, that those departures are small enough to be consistent with current data. In some cases, this leads to distinctive signatures that future observations might pick up. A bounce that passes through a contracting phase with particular properties can imprint a slight asymmetry between large and small-scale fluctuations, or a small amount of non-Gaussianity in the pattern of temperature anisotropies. Certain collision scenarios might leave directional imprints or specific spectra of primordial gravitational waves. This is why cosmologists care so much about the tiniest details in the microwave sky, and why experiments that try to detect the faint hum of primordial gravitational waves are pushed to such extremes. They are not only checking whether inflation happened, they are listening for the echo of whatever, if anything, came before. At the same time, there is a built-in limit to what we can hope to recover. Some quantum cosmological models display something that is sometimes called cosmic forgetfulness. The bounce, or the high curvature transition region, does not only connect two phases, it scrambles information about the earlier one. Like a chaotic mixer, it can erase detailed memory of what the pre-bounce universe looked like, leaving only a few global parameters imprinted on the post-bounce cosmos. If that is true, there may be a fundamental horizon on our ability to reconstruct the pre-Big Bang story, even if the universe itself had one. Not because of practical limits, like the sensitivity of instruments, but because the physics of the transition itself washes out the information. There is something quietly sobering about that. The early universe, in these models, is not just far away in time. It is hidden behind a process that may, in principle, be lossy. We might detect that a bounce or a higher dimensional event occurred, infer some of its broad properties, and still never be able to say in detail what the previous phase contained. You could take that as a defeat. Another wall, just with more mathematics in front of it. Or you could see it as another iteration of the same theme that runs through this whole question. Every time we push our descriptions toward the edge, we discover that the categories we began with are too simple. Once, the tension was between a static universe and an expanding one. Then between an expanding universe with a beginning and one with eternal inflation. Now between a classical singular bang and a quantum bridge. Each time, the frontier shifts. It becomes less about a single fact and more about the structure of the theories themselves. From a human point of view, lying awake at night, there is an odd comfort in this. We are used to imagining that the universe must either give us a clean origin or refuse entirely to say. Quantum cosmology suggests a messier, more realistic middle ground. The universe may not have a single magic starting point. The Big Bang may be the visible tip of a more complex transition. But the details of that transition, and of whatever lies beyond it, might be partly shielded from us by the very processes that made a universe like ours possible. The aim of all this work is not to decorate ignorance with fancy words. It is to take seriously what the singularity theorems already told us. That classical general relativity, left alone, predicts its own demise in certain regimes. The gentle bounces, the higher dimensional collisions, the limiting curvature caps, are attempts to sketch what might lie on the other side of that demise, without abandoning the discipline of testable physics. If there is an emotional summary to draw, it might be this. General relativity describes a universe of astonishing flexibility, where space-time bends and stretches in response to matter and energy, yet insists on breaking under infinite stress. Quantum gravity, in many of its guises, whispers that the breaking point is an illusion born of treating the fabric as too simple. It suggests that, near the most extreme conditions, the weave tightens, the threads change, and the cloth refuses to tear in the way our first classical glance would have predicted. So when we say that quantum gravity prefers gentle bounces over infinite bangs, we do not mean that the universe is kind. We mean that, at its hardest edges, the mathematics seems to favor resilience over rupture. In that light, the Big Bang becomes less a single, violent punctuation mark and more a region where two ways of being meet. On one side, a universe governed by familiar rules, expanding and cooling, forming stars and minds. On the other, something we are only beginning to name, where space and time themselves are not yet what we take for granted. General relativity tells us how far that familiar regime can be pushed. Quantum gravity, Whatever form it finally takes will tell us how the story threads itself through the place where the old equations fall silent and continues. Once you start thinking about the Big Bang as a bridge instead of a wall, another possibility quietly appears at the edge of the picture. What if that bridge is not unique? What if our whole observable history is just one span in a much longer chain of crossings? Some years ago, one of the most audacious versions of that idea arrived in a very concrete form: a pattern of circles on a map of the sky. When the cosmic microwave background was mapped in detail, the data were not just beautiful, they were dense. A nearly uniform glow, dust foregrounds, instrumental noise, and, laid over all of that, a mottled pattern of tiny hot and cold spots. Most analyses treated this as a random Gaussian field with a particular power spectrum, just as inflationary cosmology suggests. But Roger Penrose and collaborators went looking for something more specific. They claimed to find families of concentric circles in the microwave background, regions where the temperature fluctuations were unusually low in variance, nested like ripples in a pond. In their interpretation, these were not accidents. They were scars. Traces, they suggested, of unimaginably energetic events in an aeon before ours. Collisions of supermassive black holes radiating gravitational waves that, over a timescale beyond ordinary thought, left faint imprints that survived the death of their universe and slipped through into the next. This is the seed of what Penrose called conformal cyclic cosmology. In that picture, the universe does not have a single birth and death. It proceeds through successive aeons. Each aeon is a complete cosmological history, a hot early phase, structure formation, long stellar evolution, black hole growth and evaporation, and finally, a very cold, very dilute future dominated by massless particles and effectively scale-invariant physics. The mathematical trick at the heart of this idea is to notice that when a universe becomes extremely empty and its material content loses any notion of a fixed mass scale, its geometry can be rescaled without changing the physics. Penrose proposes that the infinitely expanded future of one aeon can be stretched and squashed, conformally rescaled, into the Big Bang of the next. The end of one cosmos becomes, after a change of units, the beginning of another. No absolute beginning. Only a chain of cosmic lifetimes, each one an aeon linked to the next. At this strange boundary where time looks, geometrically, both like an ending and like a start, it is a breathtaking image. Black holes, as long-term actors, whose final evaporation helps erase the mass scales needed to glue aeons together. Concentric rings in the sky, as whispers from events that took place before our own Big Bang. It is also deeply controversial. When the concentric circle claim was published, around the year 2010, it did not sit quietly. Other researchers, working with the same microwave background datasets, set out to test it. They generated mock skies using standard cosmological models, passed them through similar analysis pipelines, and asked how often patterns at least as striking as those reported by Penrose's group would appear by chance. Their conclusion, broadly, was that the circles were not statistically exceptional. In other words, if you look for concentric low-variance rings in skies generated by the usual inflationary LCDM model, you find them about as often as you find them in the real sky. The patterns are consistent with randomness, once you account properly for how many places and scales you search. From the point of view of mainstream cosmology, that was a strong blow. The specific observational hook that had made conformal cyclic cosmology famous in public discussions was, if those counter-analyses are right, not the smoking gun. It first seemed to be, yet there is something important in the way this all unfolded. A radical claim about a universe before the Big Bang was not simply dismissed as philosophy. It was translated into a concrete prediction. Look for particular statistical features in the cosmic microwave background. Data were checked, methods were scrutinized, other teams weighed in. The result may well be that the original evidence does not hold up. But the larger question it raised remains: sharpened rather than dulled. If there were aeons before ours, what would genuine fingerprints of their existence look like? Could they survive the violence of transitions between phases? Could they hide in subtle correlations in the sky? In the spectrum of primordial gravitational waves? In patterns of ultra-large-scale structure? Penrose's proposal is not the only way to imagine cycles. Other ideas, like ekpyrotic scenarios, picture the universe moving through repeated bouts of slow contraction and hot expansion. In some versions, a long, smooth period of contraction with special properties prepares extremely homogeneous conditions, which then rebound into an expanding phase that can mimic inflation's successes. The cycles can be endless in principle. The cosmos breathes, ever so slowly, across spans of time far beyond any star's life. Still, other cyclic models merge the brain collision stories with ekpyrotic smoothing, producing a universe where each bang is not a creation but an event in an ongoing, higher-dimensional rhythm. All of these modern cycles, whatever their mathematical differences, rhyme with something ancient. Long before satellites mapped the microwave background, human beings suspected that time might not have a single, linear arrow stretching from a unique beginning to a final end. In Hindu traditions, the universe passes through kalpas, vast cycles of creation and dissolution, unfolding on timescales that dwarf human history. In some strands of Greek philosophy, there are motifs of eternal recurrence, worlds that burn and are reborn, configurations that return. These are not scientific theories. They are stories, metaphors, attempts to express a sense that reality might be too large, too self-referential, to fit inside a single narrative arc. The fact that modern cosmology finds itself by a completely different route, exploring models where universes may repeat or give birth to new ones, does not validate the ancient myths, but it does show that the intuition that one birth might be too small a canvas is very old. There is, however, a hard technical problem that haunts cyclic models, old and new. Entropy. Each time something irreversible happens in a physical system, heat flows from hot to cold, structures break down, information is lost into black hole horizons, the entropy increases. In a single, expanding universe, this is the familiar second law. The total entropy tends to grow. Stars burn their fuel. Temperature differences even out. Structures eventually dissolve into a more uniform, high entropy state. If the universe goes through cycles, what happens to that accumulated disorder? If every aeon starts with a low entropy beginning and ends with a higher entropy end, then successive cycles would seem to carry a growing burden of irreversibility. Later cycles should be more and more washed out, more and more disordered. Yet we find ourselves in a universe that, at least in its early stages, was extremely ordered, low entropy, smooth, with delicate conditions that allowed complexity to form. Any viable cyclic cosmology has to face this. Some try to reset the entropy budget by spreading it thinly over an ever-growing volume at the end of each cycle, making the entropy density small enough that, after conformal rescaling, the next aeon can look young again. Others invoke subtle quantum effects or special boundary conditions that effectively erase part of the entropy between cycles. Whether those mechanisms are convincing is part of the ongoing debate. What matters for our quiet journey is that the question of cycles is not only romantic, it is tied to some of the sharpest arrows in physics. The direction of time, the nature of gravitational entropy, the fate of information. If you step back from the equations and just hold the images, the contrast is striking. A universe with a single Big Bang and no predecessors is an orphan story. There is one great rupture, one luminous beginning, and everything that happens is downstream of that lone event. You can ask why its initial conditions were the way they were, but there is nowhere earlier in the same physical framework to go. A cyclic or aeonic universe is different. It feels less like a solitary autobiography and more like a family saga. Each aeon has its own character, its own internal dramas, its own rise and decay, yet they are linked. The end of one leaves faint scars, perhaps in the beginning of the next. Black holes in a prior aeon might, in Penrose's imagination, leave those concentric halos in the microwave background of ours. A contracting phase in an ekpyrotic model might set the conditions for the smoothness of the next expansion. In such a cosmos, our Big Bang would be a chapter heading, not page 1. Our birthday, as a universe, would be one date among many, on a longer calendar. The night sky then becomes even stranger. Not just a record of our own cosmic childhood, but possibly, in some almost invisible way, a palimpsest of stories written before our time. Most of the marks we see the distribution of galaxies. The pattern of microwave fluctuations are fully explicable within a one-off Big Bang plus inflation picture, yet hidden among them, in principle, could be scars of universes that lived and died before ours. Right now, the evidence for such scars is weak at best. Many of the specific claims have not survived careful statistical scrutiny. The cyclic models themselves come in many flavors, and none has the kind of empirical support enjoyed by the simpler LCDM plus inflation framework. And still, the fact that we can even pose the question in a testable way is astonishing. We can write down concrete predictions about how pre-Big Bang events might perturb the statistical isotropy of the microwave sky, how they might seed particular non-random features, how they might alter the spectrum of primordial gravitational waves. We can design experiments on this small planet to look for those patterns. We can rule out some possibilities and tentatively allow others, whatever the final answer turns out to be. That ability to take the idea of other aeons and turn it from metaphysical speculation into something that can, in principle, be confronted with data is a quiet revolution. It leaves us with a human question that is harder to put away. If our universe is one among many eons, if our Big Bang is not unique but part of an ongoing sequence of cosmic lives, what does that do to our sense of meaning? Does it make us feel smaller, as if our entire history is just one episode in an endless series? Or does it offer a different kind of belonging? The way learning that the Earth is one planet among many did not erase our value, but reframed it? Perhaps the answer is less about the number of aeons, and more about what meaning has always really been. Something created locally, in finite minds, under particular skies, regardless of how many times the universe has breathed before. Once you let the possibility of other aeons in, something quieter happens. The question turns around. It stops asking only what the universe is doing and starts asking what these stories are doing to us. The first thing to admit, with some calm honesty, is that none of this has dethroned the Big Bang in the place where it is genuinely strong. The evidence for a very early, hot, dense phase is overwhelming. The expansion of space, written in the redshifts of galaxies. The microwave afterglow spread almost perfectly across the sky. The primordial mix of hydrogen and helium forged in the first delicate minutes. All of that still points back to a universe that was smaller, hotter, and more tightly coupled than anything we can reproduce on Earth. In that sober sense, the Big Bang remains our best account of the young cosmos we can actually see. What has changed is the confidence with which we can declare it to be the first page of everything. Singularity theorems tell us that our classical description runs into a limit. Not necessarily that reality began there. Inflation opens the door to larger structures in which our hot phase might be a local event. De Sitter extensions and their fragile coordinate horizons show how the apparent beginning could be a wrinkle in our chart, at least in special cases. Quantum gravity models soften the infinite spike into a bounce or a rounded bridge. Taken together, they suggest a different way to phrase what the Big Bang is. Not the moment something emerged from nothing, but the edge of a regime where our present combination of general relativity and particle physics can still speak clearly. Beyond that edge, the language changes. The story may continue. The astonishment is no longer that we have located the moment when everything started. It is that our current theories have carried us far enough to see the boundary of their own reach. From there, another fact comes into focus, and it is more unsettling. The question, did the universe begin, sounds simple in our everyday grammar. It assumes that time is a kind of container that either has a closed end or stretches back without limit. But much of the work we have been walking through hints that this may be the wrong kind of question altogether. If time itself is emergent, if it arises as a coarse description of deeper structures that do not, in themselves, come labeled with a before and an after, then asking what happened before the Big Bang is like asking what happened north of the North Pole or what the temperature of a single atom is. The words are familiar, the sentence is grammatical, but the concept you are trying to extend has reached the place where it no longer applies in the same way. In some quantum gravity ideas, the region we call the Big Bang is not a moment in time but a transition in the underlying degrees of freedom. The way liquid water turns into steam, you can ask what lies on either side of the phase change. It makes less sense to ask what the phase change itself was doing, as if it were just another day on a calendar. In conformal cyclic cosmology, the question of a beginning evaporates in a different way. Time does not stop or loop back. It is stretched and redefined so that the infinitely expanded future of one aeon and the hot origin of the next are the same geometric surface, seen through different conformal lenses. There is no time outside the chain of aeons in which something else could be said to have happened. This does not mean that questions about origins are meaningless. It means that their shape might have to change. Instead of demanding a yes or no to "did it begin?", we may have to ask, more modestly, how far can our notions of before and after be extended? And in which regimes does it stop being useful to think in those terms at all? Behind both of these shifts lies a third fact, and it is perhaps the strangest of all. The most astonishing part of this story is not whether the universe began. It is that a creature on a small rocky planet can ask the question in a way that forces the world to answer with theorems and data instead of silence. Think of the dates as markers in a long, careful improvisation. In November of 1915, Albert Einstein writes down the field equations of general relativity, inviting the idea that space-time itself can bend and evolve. A little more than a decade later, Alexander Friedman and Georges Lemaitre find expanding solutions, and in the year 1929, Edwin Hubble measures redshifts that tie those solutions to the sky. In the middle of the 1960s, a faint hiss in a New Jersey antenna becomes the cosmic microwave background, turning the hot early universe from theory into observation. Around the beginning of the 1980s, the idea of inflation rises, first as a way to iron out puzzles in the Big Bang, then as a source of the tiny ripples that seed structure. In the early years of the 21st century, the Borda-Guth-Vilenkin theorem sharpens the notion of a past boundary in any eternally expanding universe. Around the year 2010, Penrose and collaborators point to circles in the microwave sky and say, perhaps too boldly, these might be echoes from before our bang, triggering both excitement and rebuttal. In the early 2020s, work on curvature singularities and extensions in inflationary models explores, with increasing technical finesse, which histories can pass smoothly through the would-be origin and which cannot. Across that one human century, the narrative of the beginning has been written, erased, and rewritten, not in scripture but in a dialogue between equations and evidence. At each step, we walked a little closer to the edge of our map. At each step, the edge moved. It would be easy to treat all this as a distant game, something that concerns only the universe at large. But when you sit in the dark and listen to these possibilities, another layer appears. The question of whether the cosmos has a first page is tangled, quietly, with how we feel about our own last page. If the universe had a single sharp beginning and will someday end in some final silence, our lives happen between two absolute bookends. If the universe has no first moment, if it cycles through aeons, or blooms eternally in some inflating background, then our birth and death are framed differently. We are local, finite. Our beginnings are not aligned with the universe's birth, and our endings are not timed to its death. For some, that makes existence feel smaller. For others, it takes weight off the question. If reality itself may never have had a single starting gun, perhaps it is less urgent to pin our meaning to any imagined cosmic intention. Meaning can be something we construct in the middle of an unfinished sentence, not something we inherit from its first word. there is a gentler comfort there. Not the comfort of an immortal universe that guarantees our significance, but the comfort of living inside a story that is large enough to contain its own incompleteness. A story where even the Big Bang, that canonical opening, is a chapter that can be revised as our understanding grows. You can see that acceptance rehearsed in our art. In the film 2001, A Space Odyssey, a bone thrown into the air cuts to a spacecraft, and the gap between those images holds unspoken aeons of evolution. In Interstellar, a fall into a black hole opens into a tesseract of possibilities, not an end. Artists inspired by cosmology draw impossible staircases and recursive universes, like Escher projections of spacetime. Composers write music that swells and dissolves around themes of origin and return. Long before we had the technical means to calculate geodesic incompleteness, we were practicing how to live with open endings in image and sound. So maybe it is fitting to return, at the close of this journey, to something as small as a headline. Sometime in the year 2010, on a screen somewhere, a sentence appears, a suggestion that there might be signs of a universe before the Big Bang in the microwave sky. Whether the specific claim about circles survives or not, it does something real for the person reading it by a window at night. It cracks, just a little, the feeling that the story of everything has already been fully told. That crack is still there. Maybe the universe did not start with the Big Bang. Maybe it did not start anywhere at all. But tonight, it continues in your breathing, in our thinking, and in the question we keep turning over. At the edge of the map, what else is there?